Okay, in this lesson we're going to look at Newton's laws, still sticking with Newton's laws, and I want to talk about three new kinds of forces. The first force I'm going to talk about is what we call a drag force, or air resistance or something like that. A drag force, but it can be also in a liquid. A drag force is the resistance force caused by the motion of a body through a fluid, such as water or air. One thing that happens as the speed of an object increases, so does the drag force acting on it. On a calm day you go cycling, you feel the air resistance in your face, the wind dragging across your face. As you speed up on the bicycle, you can feel that drag force increase. Okay, when that drag force equals to the force driving me forward, well, we get to what we call a terminal velocity. Okay? So terminal velocity is when the drag force matches that propulsive force driving me forward. We usually get it when we think about something falling from a great height. Terminal velocity, the speed of the object as it falls, increases until such a time as the drag force matches the force pushing the object towards the center of the earth. And at that point we get something called terminal velocity. The object cannot go any faster. So I'm 70 kilos. If I go skydiving, what will the drag force be when I reach terminal velocity? So if I'm 70 kilos, I'm going to draw a little force diagram just to kind of model this. If I'm 70 kilos, there's my force diagram. That's me. That represents me. What will the drag force be when I reach terminal velocity? So what we've got to think about, first of all, we're going to think about what forces are acting on me as I go skydiving. Well, one force, I suppose, that's acting on me is the force exerted on me by gravity, which is called the weight. Okay, so the weight force. Your weight force is the force exerted on you by gravity. And the force exerted on anything by gravity is its mass, the mass of the object, times little g, the acceleration due to gravity. So if I weigh 70 kilograms, well, that means my weight will be 70 g newtons. Okay? In fact, people would say, what's your weight? Lots of people say 70 kilograms. 70 kilograms is actually your mass. Your weight in that case would be 70 times little g, which is about 700 newtons. And so your weight is about 700 newtons if you're 70 kilos. So that's my force. So I drop, I go skydiving, I jump out of a plane. That's the force driving me downward there towards the center of the earth. There's a force of 70 g newtons, which is about 700 newtons, taking g to be about 10. As I travel downwards, what happens? Well, I gather speed, and as I gather speed, what happens is the air resistance to my motion increases. The drag force increases as I'm dropping towards the earth. And as that increases, this weight is constant. That's not changing. My weight is always 70 g. That's the force exerted on me by gravity is always 70 g, more or less. So what is changing is the drag force. And, initially there's kind of no drag force, and then there's a little drag force, and then the drag force kind of grows until such a point as it matches my weight. So at some point, when I achieve terminal velocity, what will happen is my drag force will have increased to 70 g newtons. So if I go skydiving, the drag force will be 70 g newtons when I reach terminal velocity. At that point, when it does that, well, the force downwards on me is 70 g, the force upwards on me is 70 g. I am no longer accelerating. I don't stop moving, of course. I'm just traveling with a constant velocity now downwards, but the down force and the up force are equal, so there's a net force of 0 at that stage, which means there's no acceleration. Remember, acceleration can only take place if there is some net force on the object. How do skydivers increase their drag force? Well, maybe that's something to think about going forward. How can we increase our drag force? And why would you want to increase your drag force? have a think about those questions. Okay. Another force I want to talk about is something called the normal force or the normal reaction. Okay? In mathematics, normal always means perpendicular to. The word normal means perpendicular to. So the normal force is the component of a contact force that is perpendicular to the surface that an object contacts. So any time two objects are in contact, there is a normal reaction, there is a contact force, a normal reaction. A man leaning against a wall, well, there's a normal reaction acting against the man. The force on the wall, on the man by the wall, is to the right. So that's the force on the man by the wall. Obviously the force on the wall by the man is equal and opposite to that. So the wall is exerting a force on the man perpendicular to the wall, and that's called the normal reaction. We usually use the letter N or for those things. If I look over here at this kind of desk that I've just Googled a desk, we have 4 points of contact on the ground here and 4 over on this side. At each of those points of contact, we have a normal reaction. And assuming the weight of the table is equally distributed, all those reaction forces will be equal. And that's what's happening there. Here's a ladder leaning against a wall in the bottom picture down here. Well, there's a normal reaction on the ground. The ladder is pressing down on the ground, so the ground is pushing back against the ladder. That's my normal reaction there. Normal reaction. But also the ladder is pressing against the wall, so there's also a normal reaction that way. I'm going to use the letter or for that one. So we've got a normal reaction up and a normal reaction to the right. The ladder is pushing against the wall is pushing against the ladder. Newton's third law. For every action there's an equal and opposite reaction. The ladder is pushing down against the ground, so the ground is pushing back against the ladder. So there's 2 reaction forces there with the ground. The last force I want to talk about is what we call the friction force. Okay, and friction is a force that opposes the motion of an object. So this is an important word here. Friction only, is always going to oppose the motion of an object. If an object is not moving, or not trying to move, I should say, well then there won't be any friction. If I'm trying to move an object, for example, slide this big box across the floor here, there's going to be friction. Okay? Note, as this person pulls on the rope here, he's creating a tension force going that way. So there's a tension force going that way. If the ground was smooth, there'd be no friction force, but the ground is not smooth. There will be some friction force here, and it'll be acting in the opposite direction to the intended motion of the object. Okay. Now, friction can prevent motion, so you might find that friction can occur to objects that are not moving. For example, if this box was just too heavy for the man to pull to the right, well then friction would be preventing him pulling. Okay? It's friction that is stopping that happening. So if he tries to pull this and he's not able to move it, well, friction is to blame. That's why he can't move that object. The amount of friction on an object, an object can offer really depends on 2 quantities. Okay, so friction is dependent on 2 quantities. The first quantity is the mass of the object. So a bigger mass will mean more friction. The bigger the mass, the bigger the friction. Okay, smaller mass, smaller friction. Okay, friction and mass are, proportional to each other directly. And the second quantity that friction depends on is something called the coefficient of friction, which is usually denoted with this letter. Here it's a Greek letter, and you may have seen it before. It's mu. So the coefficient of friction is mu. And the friction force in an object, the most friction that an object can call upon, the maximum friction, let me write F max. The maximum friction is whatever mu is multiplied by what we call the normal reaction. Okay, and that's something that you're going to wrap your head around. Now again, if you look at this picture, you know, when the man starts pulling slightly on the rope, friction will prevent him pulling this box maybe to the right, and there's a small friction, but the more he pulls, the harder he pulls this rope, the greater the tension will be. Well, that's going to increase friction. So friction increases as tension increases here, until such a point where friction can no longer offer any more value, where it reaches its maximum value. So friction will increase here as tension in the rope increases, until friction can no longer increase, and friction can no longer increase when it reaches this value here, mu times R. Mu is the coefficient of friction, R is the normal reaction, and the normal reaction depends on the mass of an object. The coefficient of friction really is dependent on other things like what materials are involved. So if I wanted to manufacture car tires, I would want to have a high coefficient of friction so that when I hit my brakes the car stops. Okay, if I want to manufacture ice skates, I want to have a low coefficient of friction because I want the skates to slide nicely on the ice. Okay, so when two surfaces combine, I suppose what they're made of is going to determine what the coefficient of friction is. So the mass of the object and the coefficient of friction. That's what determines the friction force. If I look at my ladder problem again here, we've got a ladder, and I want to think about all the forces at work on this ladder, you know. Not a force diagram as such, but just think about all the forces at work on it. Well, we've got this ladder pushing down on the ground, so the ground is pushing back on the ladder. And it's a normal reaction. We have gravity pushing down on the ladder. That's the weight of the ladder, whatever that is. The ladder is pressing against the wall, which means the wall is pressing back against the ladder, perpendicular to the wall. That's another normal reaction. And suppose the ladder is not slipping. Or in fact, let me say, suppose the surfaces are rough, okay, as opposed to smooth. So there is friction. What direction will friction be acting? Well, you know, the ladder, if there was no friction, the top of the ladder would slide down the wall, the base of the ladder would slide out. So friction is going to oppose those directions. So if the ladder is trying to slide down the wall, well then friction will be acting upwards. Let me call that F1, friction acting upwards. Also the base of the ladder without friction would slide out to the right out there, which means friction is acting out there to the left. So F2. And they're all the forces at work on that ladder. Go through them again. Gravity pushing down on the ladder, that's called the weight of the ladder. The weight is the force exerted on an object by gravity. The normal reaction here with the ground. Remember, the ladder is pushing onto the ground, so the ground is pushing back up against the ladder. The normal reaction here at the wall. Remember, the ladder is pushing against the wall, so the wall is pushing back against the ladder. And then the friction force opposing motion here. The ladder is trying to slide down the wall, so the friction is acting against that, upwards. And the ladder is trying to slide to the right, so friction will be opposing that, assuming those surfaces are rough. Okay, that's it. So get your head around those forces, make sure you understand those new terminologies, normal reaction, friction, and drag. We'll be talking about some of those things in our next lesson.